Let's get going. Oh. One second. All right. So we are on, getting closer to the end. We're on lecture 16. And today we are going to just pick up right where we left off last time. So, just as a recap, the last topic we talked about in the previous lecture is on decision trees. And we looked at essentially how that works, where you're doing two things, right? We are selecting the variable at every, we're selecting the variable and the split at every node in order to get kind of closest to our outcomes as possible. And we saw this example, and at the end of class, right, I showed that if we change the sample, that you change the draws that you use to build the tree, you can actually get wildly different trees, right? And that can actually affect your predictions in big ways. So that's one of the drawbacks of the decision tree. Otherwise, it's actually a fairly powerful tool. And so what we're going to start off with today is addressing specifically that deficit, right? So the idea that you have very high variance with decision trees based off of the sampling procedure. So how can we get around that? And the first thing I'll talk about is this idea known as bagging. So this actually stands for bootstrap aggregating. Okay, so the idea is if one tree is unstable, why not fit many trees and average the prediction? So the idea is if you have B observations, each with a variance of sigma squared, the variance of their average is sigma squared over B. Okay. So the idea is I have a tree that has some amount of variance. If I have many trees, I can average predictions together and get to a lower variance. This is maybe a little sloppily written, so I'll write that again. So sigma squared. However, in order for this to be true, the observations must be independent. Okay? So we will get to this idea in a little bit. So let's talk about the algorithm behind bagging. So here we are going to draw B bootstrap samples. Does everyone know what a bootstrap is? Right, so this is the, so essentially I'm getting draws from a known sort of data set, right? And so whatever our data is, in order to build the tree, in order to build multiple trees across one data set, we're essentially going to randomly select from that data set, build a tree, and then randomly sample from that data set, build a tree, and so on. Okay, so we're going to draw B bootstrap samples from the training data, which means I end up with B number of trees at the end. So sample and observation with replacements B times. I'm going to then fit a tree on each bootstrap sample. And actually here, I'm not going to do any post-process pruning, right? So we talked about how we will prune them back as a way to avoid overfitting. Well, in this case, since we're building many trees, let's say many overfit trees, when you do the averaging and produce new predictions, that's going to accommodate the fact that you have this like variance happening from these multiple trees, and then we're going to be sort of automatically reducing that, right? So remember, overfitting is a byproduct of the variance, and the averaging helps to get rid of that. So we're essentially reducing the variance and / or the overfitting in a slightly different way than we have before. Okay, so average the B predictions. So this would what you would be doing in a regression outcome, or take a majority vote for a classification outcome. Okay, so what does averaging actually mean? So the idea is we have a bunch of trees that we've built. How do I average them together? So what you do is you take a new observation, let's call it X, and produce a prediction with every tree, and then combine into one. So in the regression case, we do the arithmetic mean. So this would be something like f hat bag of X over 1 over B equals 1 up to B F of BX. This, all I'm doing is doing the average prediction, right? So imagine our previous example, right? We built a tree, and then I think the first one that I built, it said in the root node, we split on price, and then we split on other things, and then we split on other things. That would be one tree that I've built from the sample. And then in another bootstrap sample, maybe the root node, I think a different one was like the shelf location, and then it splits that, then it splits price and whatnot. And then you maybe have another tree and another tree and another tree, right? So you have, let's say, 1,000 different trees. So the idea here is let's take an observation. Let's just say, okay, what if I wanted to know whether or not, or what the sales would be if, you have price A, shelf location B, yada, yada, yada. I'm going to drop it down every single tree. Okay, I have 1,000 trees, and I'm going to predict based on tree A, tree B, tree C, tree D, that one observation. And so I'll have 1,000 different predictions of what the sales would be, and I just average it. Okay? So that's what you would do here in the regression, in the classification. You would just do majority vote or probability averaging. Right? And so our example last time was, we said if the sales were above 8,000 or if the sales were below 8,000, it's like high or low sales. So now I do the same thing. I have some row of data that has, price X, shelf location Y, yada, yada. I drop it down every tree, and now the tree will tell me, in this case, it's a high sales or low sales, high sales, low sales. And then I look at the one that has the most count, and that's my sort of average outcome. Or it could be a probability of high sales or low sales, and then you could do a probability-based averaging. Okay? All right, any questions about this? Right, so this is really essentially the same thing as what we had done, except now you have many trees and my predictions are averaged. And the whole idea around that is to deal with that issue of variance, that maybe the way that I sample will result in different trees. Okay? So let's take a look at implementation. So we're going to do example of bagging. All right, we got a bunch of libraries to load again, ISLR2. This time we're going to have a package called random forest, our part, which was from last time, dplyr, and we'll do ggply. Okay, we're going to set up our data from last time as well, car seats. And then if you have it handy, you can just copy and paste it. But I'm just going to set up our classification example where we had a variable called high, which was describing if the sales were greater than 8,000. Okay. Let's set a seed so we all get the same thing. And then I'm going to set up my training and testing data. So I'm making an index for all of the data that I want to be in the training sets, and I select on that. And for test, for the testing set, I grab everything that's not that index value. Okay, we're working a little bit backwards here. P is going to be one of the parameters that I set in my random, in my bagging, or it's going to be the random forest function. Okay, let me back up for a second. We started with decision trees. We're now talking about bagging. The next thing we're going to talk about are random forests. And random forests are very similar to bagging, except they change one little thing. So there's a parameter that's set in the random forest function that would then essentially be doing bagging. So I'm going to talk about that later when we get to random forests. So just hold off on wondering what line 18 is and the input, and we will get to that. So high minus sales. Data equals train. M try equals P. Entry equals 500. Importance equals true. Okay, so that M try thing that I'm setting equal to P, we're going to talk about that later. All you need to know right now is that whenever I do a split, right, I am making a decision about which variable and where to split on at every node as I go down my tree. In the bagging procedure, this lets me set every variable as one of the things that could get chosen. Okay, so that's what's happening with mtry. Okay, so let me run all of this stuff. Okay, boom, boom. Oh, shoot. Data car seats. Car seats not found. There we go. Oh, did I not load my libraries? Thought I did. All right. Okay. So we've got this going. I can print this. So here, oh, number of trees, this is the big B, right? This is how many trees we bootstrapped. We made 500 trees. Okay, and so with a decision tree, the inference is maybe a little bit more straightforward, right? We showed a diagram of the tree last time, right? Hopefully you guys remember that. I can't do that anymore because we now have 500 trees. So there isn't a good way to do visualization. The main metric that they're looking at here is prediction accuracy. So we can look at our test accuracy, prediction using bagging. If I do many trees and average across, okay, I get an average accuracy here in my classification example of about 81.5%. Okay? I don't know if you guys remember from last time, this number is higher than our decision trees. Our decision trees were like 76, 77% accurate. So bagging has helped with this. Oftentimes, the averaging across many trees will typically, well, I mean, you can expect it to be better sometimes and worse sometimes, but the more important property is that the variance has decreased. And so it's likely that we're also doing better on our overfitting task compared to our decision trees. Okay? Yeah.
I'm having a hard time visualizing this. So how do you, when you're averaging, do you get to choose the number of leaves you're remaining? Well, you have only yes or no, right? But in the examples from the other class, you had several yeses and several no's. So how do you just end up with two if you're averaging a tree that has so many leaves?
Yeah. It's not that you end up with 2 leaves, it's that the prediction outcomes are like right or wrong. So let me do an example. Okay. This is off the top of my head, so bear with me. Oh, you know what? I can do the example that we did last time. So income and own a home, and these going to buy an EV. So I think, so you might have something like root node income greater than or equal to 90, and then, yes, no, and then we have own home, like this, right? Yes, no. Now, let's say you do, and okay, instead of, well, okay, no, we'll stay here. Okay, now, instead of just having one tree, let's say you bootstrap many times, and you end up with many other trees, and maybe one tree looks like this. Own home, yes, no, and then this one is like, income, let's say greater than or equal to 70. Yes, no. Something like this, right? Yeah, so you have many, many trees that were bootstrapped from the data. And so this is an example where I have 2 trees. So how do I actually average them together? So now we take an individual observation. Let's say I have an observation where, in the data, I have income and then own home. And let's say there's one row with yes here, and let's say the income here is like 95. Okay, so what I'm going to do is I'm going to take this row, and I'm going to drop it down this tree, and I'm going to drop it down this tree. Okay, so this, okay, am I income greater than 90? Yes, so I go here. Do I own a home? Yes, so I end up here. And then here, and this is like, oh, will you buy an EV? So I end up with yes, right? Here, do I own a home? Yes, I go down here. Is my income higher than 70? Yes, it is, so I end up here. So sometimes, so this would be like a classification example. Sometimes on some trees, maybe it's no, but on, let's say I have 1,000 trees, and let's say like 900 times it says yes, and 100 times it says no, then I can, if I'm doing majority vote, then I would say the answer is yes. And if I'm probability averaging, then then the answer would be like 90% or something like that. Does that make sense? Yeah. So that's what bagging is. It's instead of looking at one tree, it's like looking at many trees, and the average is in reference to, on the average prediction that I make, like how good is my outcome? Yeah. Any other questions? Yeah. So that's bagging in a nutshell. But I had, oh yeah, I should just stay over here. I had a little caveat to this, which is this. Are the trees actually independent? So, actually, let's just start a new page here. Suppose I have this table, y, x1, x2, x3. And I bootstrap this into B trees. What is the top split for tree B1, for tree B2, for tree B3, and so on? And the question is, do we expect that tree B1 is going to split on something, and then B2 is going to split on something, and then B3 is going to split? So the root node, are they going to be evenly distributed across the variables? Probably not, right? So probably probably the same variable or set of variables. So if you think back to the car seats example, I changed the sample, right? And I said, and then we looked at what happened to the tree. So the first time I did it, it was like splitting on price as the first one. And then I think in the next one we did it, it was splitting on like shelf location. There were like 10 or 11 variables, right? And then if we do it more and more, you'll see that, well, actually, it's not like that top node is distributed evenly across those 11 variables. Oftentimes it's like price or the shelf location, right? And that makes sense. There are probably certain things that contribute more to the outcome than others. But that means that the predictions are likely to be correlated, right? Because if I use the same root node every time for a tree, then all the stuff coming out of that is probably related to the fact that I chose, price as the first node. Therefore, this idea that we have our variance decreasing to this is probably not correct. And so in reality, if you do have correlations, it'll probably look more like this. Okay? Where rho, the thing that looks like P, rho is pairwise correlation. So we may not get the sort of full benefits of doing this bagging procedure because the trees end up getting correlated. So what is a way that we can deal with this? And so in a similar way that we talked about like the evolution of models, we went from decision tree to bagging to deal with the variance issue. And from bagging, we go to random forests. and this is to deal with this independence issue. So this is an ensemble method that builds multiple trees and merges them to provide a more accurate / stable prediction. Okay, I'm looking at this definition. I don't actually like this. This is the same thing that what the bagging is doing, but what ends up happening is when you build the tree, it does it in a different way, in a slightly different way. We are doing decorrelated trees. We are building decorrelated trees. So, random forest is really just bagging with forced decorrelation. Yeah.
What's the difference between bagging and
An ensemble is, or bagging is a type of ensemble method where you're building up from multiple trees. But ensemble, like random forest, is also a type of ensemble method. Yeah. Okay. So remember, my whole argument is that when I choose what to split, it's choosing the things based off of how well it does, right? And so there's some correlation between the outcome and that variable that gets selected. And so that's why in the car seats example, we always saw that the first root node is always price or shelf location. But what if we force it so that it's sometimes when it's choosing the variable, it's only allowed to choose from like a subset of the variables. So sometimes you're forcing it to not choose price or not choose shelf location. That's what this forced decorrelation is doing. So at each split, only consider a random subset of M predictors instead of all P predictors. Okay? So how big should M be, right? So let's say I had 20 predictors. I want to choose randomly from those 20 as a subset to allow the tree to split on. And I'm going to do this many times. How big should M be? So they have rough rules of thumb, classification. You want your M to be equal to root P. And for regression, you want M to be equal to P over 3. These are rough rules of thumbs. I actually don't, to be honest, I don't know actually where or what the logic is behind this particular selection, but generally speaking, this is what people use and it works pretty well. Okay? So this is exactly the same as bagging, but you're just constraining it so that on every split you can't choose, you're not looking over all the variables, you're only looking at a subset of the variables. Okay? Any questions about that? Yeah.
You don't pick, right, because it's random? You don't pick the variable?
Yep, it's random.
How do you know, does the thing have like the method of choosing? It's random.
It's just random. Yeah. Like when you run it, what ends up happening behind the scenes, you have 20 variables. right? And so let's say you're doing regression, so 20 divided by 3. It's going to say, okay, we're going to just pick 6 variables out of the 20 that you're allowed to split on, and then it'll just pick them randomly. Yeah. Okay. Here's another actually kind of nice feature about bagging in random forests. I didn't mention this before. You kind of get this free cross-validation. So out of bag, about 1/3 of points aren't drawn. So here, when I do, when I build the random forest, or I'm doing the bagging, when I bootstrap, you have a bunch of data, and then you randomly select from the data a bunch of times. You build a bunch of trees, right? And then you do all this stuff. That bootstrap procedure, some of those data points aren't actually selected. So roughly speaking, as a rule, you would say approximately 30% of those points aren't actually going to be drawn. So the nice thing is I don't even need to make like a training and test set. By virtue of doing the bootstrapping, I have data that's left over, and then I can just use that as my testing, right? So here you can use this for out of sample testing / validation. For large B, out of bag equals leave 1 out cross-validation. So actually what ends up happening is if your data is really big and you can bootstrap a lot, you have so much data left out, it ends up converging to look like leave 1 out cross-validation, right? So that was just as a reminder, right? So leave 1 out cross-validation is when you do like a k-fold and your k is equal to your n. So you leave 1 point out, train on everything, test on that one, leave 1 out, train on everything else, test on that one, and you do that k times, or k equals n times. And so actually, yeah, there's a nice little side benefit of doing it this way. You end up with a convergence to what looks like leave 1 out cross-validation. Okay, so plus equal, so the pros, low variance, better prediction than our other methods, right? Because you're continuing to decrease on the so with decision tree, you have variance, a high amount of variance, so your overfitting part is larger. With bagging, we have a smaller amount of variance, but because things are correlated, it's not as good as you might want it to be. And then with random forests, you get variance divided by B, and so your overfitting is even smaller, which means that, yeah, your random forest tends to have better predictions than both bagging and decision trees. So useful variable importance, we'll look at this in a bit. This is robust to noise and outliers. the main drawback here is no interpretability. There's no coefficients or anything to look at, and in fact, even the relationships to your outcome are not as clear because we're looking at across many, many trees. So unlike decision tree, where I still have something to kind of visually show you that we can interpret how decisions are being made, here it's more of a black box because it's like how the decision is made across this one tree averaged out across many, many trees. So I don't really have anything to show you outside of the predictions and then the metrics of like how accurate my predictions are. Okay? Any questions? Okay, so we're going to do implementation, although I realize I forgot to show the other example for bagging. So all it is this example of bagging was for classification. We can also do bagging example for, oh, actually I don't have a bagging example for regression. No, okay, so we're good. We are in the right place. I will do a random forest of both regression and classification. So random forest, and we're going to start with classification example. Oh, I should mention. So now going back to this thing of what P is, M try is the M variable or M parameter that I was just describing. This is how many variables amongst all of them are we going to allow the random forest to train on. And here I have my all of my variables in the data, and I'm doing -2 because there's the sales and then the high classification. So these are our two Y variables, and I'm just getting rid of those. And so if I put P here, this is the same M and P that I was just describing in the notes, then it's saying, oh, at every split, you're allowed to look at all the variables, and that's bagging. And so what we're going to see is we're going to restrict this M try in the random forest, and otherwise it's going to look exactly the same as bagging. Okay, so the default M try for classification is square root P, which we just described in the notes, right? So we're going to do random forest classification using the random forest function, and it's going to be exactly the same as in the bagging. High minus sales, data equals train, except for our M parameter, we're going to do the floor of square root of P. It's just the square root of P rounded down. We're going to do 500 trees. We'll do importance equals true. Run this thing. Okay, looks the same here. I can grab all of my class errors. It breaks it down into where you have no's and yeses, and then you have your false positives and false negatives. So if we do a prediction on this model using the test data, I can look at the error rates. Okay, or sorry, the accuracy, not the error, the opposite. So I'm getting 84.5% of my predictions correct, right? I'm going to copy and paste this bit. So if I want to compare this result that I just got, 84.5, against the decision tree and against the bagging, we can do that. So I'm just rerunning what we had from last time. So our part, so this is a single decision tree, and then the predictions associated with that. And then I have my bagging results from earlier. So I'll just run all of these guys. Okay, so single tree, accuracy of 77.5%, bagging, accuracy of 81.5%, and random forest, accuracy of 84.5%. And this is right? The setup is entirely the same. The single tree has the highest variance. The bagging has lower variance, but doesn't decrease by sigma squared over b. It decreases as a function of the correlation between the variables. So not quite as good. And then when we force it to be decorrelated, you have your best predictions because you have the lowest amount of overfitting, the lowest part of the variance. Okay? And that's reflected in the accuracy of these models out of sample. Any questions? Let's take a look. Okay, let's do. Yeah, let's do one more example. Random forest regression example. So we're going to predict sales directly. Default mtry for regression or continuous is p over 3. Okay, so RF, regression, random forest, sales, like so, data equals train. Mtry is now floor of number of columns of train minus 1 divided by 3. We're going to have 500 trees. Okay, so okay, we're going to do our prediction on our test data. And this time, we're doing regression, so it's a continuous output variable. We don't have the classification error rate, right? We have our the errors as they pertain to the size of the residuals. So what we can do is look at the mean squared error of our random forest. So we have our mean squared error. This number is only meaningful to compare against other models that use the same outcome variable. But we actually can look at the square root of the mean squared error, which operates on the same units as y. So what this is telling us is, on average, the size of error in our outcome prediction is about 1.4 or 1,400 sales of a car seat per prediction. Okay? Okay, this part we don't need to follow along. I'm going to do another comparison to the single tree. Yeah. So single tree has a mean squared error of 2.468, whereas the random forest has a mean squared error of about 2. So 17% reduction. Yeah, so random forest is a lot better than our decision trees in general. Okay, we can do a plot of the predictions here. Okay, and we can see kind of how well we're doing. The line is basically a 45-degree line. If the predictions matched our actual values, they would be on the red line. And so you can see how well your model is predicting by looking at the actual versus predicted sales. Okay. The last one is you can use this function var imp plot, which gives us the importance of the variables in the regression. So that will end up looking like this. Oh, I guess I accidentally included our classification high variable in here. Okay, so maybe ignore this one. They are, I guess, in both models, but okay. Generally speaking, this will give you kind of like a rank order of the percentage increase in your mean squared error if you were to omit the variable, and so the highest ones are going to be the most important to reduce your mean squared error as much as possible. Okay. Any questions? Yeah, so that is it for our decision trees. And we are going to now kind of continue our evolution and journey to models that are maybe a little bit more focused on prediction, right? With the trees, there's some inference based on our ability to look at like the variable importance, and with decision trees as a solo, you can have inference as it relates to the structure of the trees. And we are getting more into, maybe I'll describe as these traditional or more modern machine learning methods. So, moving on. So we're going to talk about why do we, so moving beyond splines plus kernels. So why is it the case that we don't see these types of models being used as much, right? So splines, right, semi-parametric, functionally flexible, and kernels, powerful non-parametric, for finding decision boundaries. And so we're going to look at modern machine learning methods as the next logical step. So these are going to be similar in principle to approaches we've already discussed. But in practice can be a powerful tool to handle scaling. So while the splines and kernels are pretty fantastic at what they do, one of the drawbacks is we live in an era, right, with lots of data that's available. And unfortunately, splines and kernels can become pretty computationally intensive pretty quickly. So scaling two things, so more features. We're going to start using some machine learning lingo, even though it's all just the same stuff. So features are explanatory variables. And more data. So larger n, more rows. That's part of the motivation here. The ability of splines, and kernels to deal with data that is both really wide and has a lot of rows can be difficult. So let's take a look. Let's take a look at kind of the building blocks of some of the machine learning approaches. So let's look at a basic neural network example. That replicates a linear regression. Okay. So we are getting into neural networks now. I have a node I1 and a node I2, and these both input into a node L with weights 1, 1, and 1, 2. So if I write this out as a function, looks something like this. W11I1 plus W22I2 equals L. What does that look like to you guys? Any ideas? Any guesses? This equation? Well, it's like vectorized in notation. So maybe. Any other ideas?
That's a linear regression.
Yes, I did try to give a big hint. Okay, so this kind of looks like this, right? And in fact, this would be a sort of replication of a linear regression model. We're just using machine learning terms instead. So our eyes are arranged in what are known as tensors. And so the reason why I was saying it looks kind of like a vector. So scalars, this is just a 0-dimensional tensor. A vector is a 1-dimensional tensor. Matrix, right, is a 2D tensor. And an array would just be an n-dimensional tensor. There's one other distinction that I wanted to make here that has more to do with operationalizing this neural network. In a traditional regression, so maybe if you guys recall all the way back to our very first, well, I guess not first day because we did the whole R tutorial, but the first lecture day when we first covered linear regression, there's actually a difference in the way we solve for a beta versus a W. Does anyone remember what I mentioned about this? Okay, so in a regression, we have a closed form analytical solution for calculating betas. Right, so if you've taken a econometrics or a stats class, you've probably seen this, where we have this optimization, so minimize with respect to betas, your residual sum squared, which is equal to our y minus y hat squared, sum over all of the i's. And that optimization, you're solving for the betas, and that particular optimization has this closed form solution of beta equals xtx minus 1 of xty, right? So this is a closed form analytical solution. Guaranteed the correct solution and fast in theory. Is this ringing any bells? Does anyone remember what we talked about here? Right, so I can solve for the betas instantly with this equation. What's the problem with this equation? This thing here. So a matrix inverse is a very memory-intensive process. So for a lot of what we do with linear regressions, this doesn't tend to be a problem. If you've got like 100 or 1,000 different data points, or if you're operating with 10, even 100 variables, this can solve no problem. But when we're talking about machine learning approaches, oftentimes you might have millions of data points, maybe even billions of data points or more, and you could have not 10 or 100 variables, you could have 1,000, 10,000, 100,000 variables. And that just breaks this. Doing a matrix inverse on data that large is very difficult, or I should say hard to hold in memory. So even though it's not an analytical solution, you can do something different. So weights, so our W's are obtained by solving numerically through optimizers such as gradient descent. So not nearly as memory intensive. And this can scale very efficiently and can be applied flexibly to any functional form. Okay? So that's an additional difference, at least in the way that we calculate the parameters in a lot of these neural networks. Okay, so we're gonna start layering in a little bit of complexity at a time as we kind of build up how these neural networks work. Okay? So I'm gonna draw a diagram. So we have our input that goes into some layer where I actually may undergo some kind of transformation. And that could happen multiple times. These will go to eventually some kind of predictions. So we have our y hat here. And maybe we compare this against our true values. And here we have something known as a loss function. Okay? So this is essentially measuring our errors. So a lot of times this might be like y hat minus y. And then we choose some means to, we have some kind of metric to measure that loss function through a loss score, okay? So what's an example of some kind of score metric for, let's say, for the errors that we have in our model? What's one that we've talked about all throughout the class? If I want to know something about the errors in my model. Any ideas? So the common one is like a mean squared error, right? I have a bunch of errors and I put it into one number as like a score. Okay, so this may feed back into an optimizer. And then we will calibrate our weights. And this will go back into here. Or it'll just stop. Once we're done, we'll have some weights. And so this is our weights update. And then this is our final weight. So the idea here is I have these transformations that do something to my data. I don't know exactly what's going on in these layers yet. And then those transformations end up making some predictions. I can calculate a loss score, and then using some method, I'm going to update my weights. And essentially, I'm going to continue doing this until my loss score is as small as possible, right? So this is this is kind of a rough procedure of doing this with respect to my W's, right? So we're minimizing our mean squared errors in this process. So what is this transformation? Let's go back to this thing. Okay, so we saw that earlier neural network that was just a replication of the linear regression. And what I want to do is do one slight alteration. I'm going to do this. So we end up with a neural network. This is essentially the same thing as before. Just to visualize again. But we now have this A. So A is the activation function. This allows for a non-linear transformation of the inputs at each node. So what's going on here? This is maybe a little bit of a confusing subject, but the general idea, right, what we've been doing recently is we talked all this stuff about linear regression, and then we're like, okay, let's start departing from linearity, right? I want to give the model flexibility to become nonlinear. And in the spline example, how did that happen? Well, we gave it the ability to do steps. We gave it the ability to do these like polynomial fits. We gave it knots, right? And so essentially, you're adding these things into the model to give it flexibility, to not be just a straight line. And the way neural networks do this is they provide flexibility in addition to our parameters, our W's, or what we would formerly have called betas. They do this activation function thing where they're like, okay, we're just gonna like transform the data in some weird way. Okay. So let's talk about common activation functions. So this is, again, analogous to like letting there be polynomials or letting you do not stepwise, the regressions where we can break them at different breakpoints, right? Yeah.
This is still part of the transformation part of the neural network?
Yes.
Okay.
Yeah. This is what the transformation would actually be. Yeah. Okay, so let's look at some common activation functions. So we have our identity / linear. So this is where f of x is just equal to x. And so our data would end up just looking like a line. We have a step / binary step. So this is where f of x is equal to 0 for x less than 0, 1 for x greater than or equal to 1. Okay, so we'll have something like this, 0, 0, we'll say this is 1, and we have something like this. I'll use a blue line. We have a logistic. This is f of x is equal to 1 over 1 plus e to the minus x. This would be something like 1 over here. And we would have something like this. We have tan h f of x equals e to the x minus e to the minus x. Over e to the x plus e to the negative x. And that ends up looking like this. And then we have what's known as a rectified linear unit. F of x equals 0 for x is less than 0, x for x greater than 0. This is also known as ReLU. And that looks something like this. Okay. So why am I showing us all of these? These are different ways that the input data can get manipulated, and then if you have more layers, it's like the outputs of an intermediate layer can get transformed again. And these fairly simple looking activation functions actually provide a huge amount of flexibility for your data to take on different functional forms as it gets transformed, right? So think about in the polynomial regression, we added x squared and x cubed, and that lets the line start to do wonky things, right? These activation functions are essentially doing that in maybe a little more hidden of a way. And different functions will afford different types of flexibilities. What I would say, these are very common activation functions. You know, the simple ones, a lot of times those were kind of used in the early days. Certain activation functions perform better at certain tasks. And there are drawbacks associated with activation functions. We're not going to get into, we would have to get into like some decently complicated like math to show some of this stuff. But think about it this way. Like when I did a polynomial regression, there were certain drawbacks, right? So you had like, at the edges, you had a lot more flexibility, right? And we showed ways of dealing with that. So the same thing is here. With different activation functions, there are certain types of drawbacks. And it just so happens to turn out, for reasons I don't actually maybe fully understand. So tan H and rectified linear units, ReLUs, tend to be very common activation functions that get around a lot of the traditional drawbacks that you might have with issues of like convergence and variance and that sort of thing. So a a lot of times these days, people will experiment with maybe a couple of different activation functions to see which ones help their models to perform the best. But really, what these are doing are a way of introducing flexibility into the model, combined with being very simple, right? Which is why these things can scale really well to large amounts of data. Does anyone have any questions about this? So, let's take a look at an example neural network. We're going to build up in complexity just a little bit more now. We're going to start with two inputs, I1 and I2, just as before. But now we're going to have more than one layer. Okay, so I'm going to have L1, L2, and L3. So this is going to be, so this example is what is known as a feed-forward neural network, also known as a multi-layer perceptron. Okay, so we've got something like this. Okay, so pay attention to the notation. So this one has a weight 1, 1. This one has a weight 2, 1. And this one has a weight 3, 1. Okay? So the first number refers to the node that you're going to, and the first number is the node that you're coming from. So that would make this one W what? 1, 2. Going to, and then coming from. Yes. Then this one would be W 2, 2, and this one would be W 3, 2. Okay? Okay, and these guys are each going to feed into P. So we'll call the weights here V1, V2, and V3. Okay, so we're going to build out the equation for the node just the same as what we had just done. So L1 would be equal to what? Ooh. So first off, I'm going to actually add my activation function. And then in here, it's just the things that comprise as inputs into L1, right? So A11 times, sorry, not times, of, it's a function, right? So A11 of W11 times I1 plus W12 times I2, right? So that would be this one and this one here. Then we have, so this is here, or let me, yeah, like this. Then we have L2, which is A12 W21I1 plus W22I2. So that would be this guy and this guy. And then lastly, we have L3. So this would be, hopefully you guys can figure this out now. 1,3 W31I1 plus W32I2. These two terms referring to this weight and this weight. Okay? Everyone so good so far? Good. So then finally we have P is equal to different activation function. So V1 L1 plus V2 L2 plus V3 L3. Right? So that's this guy. And then our three weights here. Okay, any questions about this? So the thing that I want you guys to take away from this is, so we're looking at this particular diagram. Consider the difference of this versus our linear regression, right? Which was essentially like this part of it. It's just the I going to the L's. Without the, actually not even that. It's, sorry, I drew that wrong. It's this part of it, right? That was our original linear regression. And in the linear regression, there's no activation function. The only parameters we have to fit to the data are our two W's, right? Or our two betas. So now, consider we have the same inputs going to a single output, but we have all this like other stuff happening in between, right? We now have 4 activation functions, and we have how many coefficients? We have, let me choose a different color. Right, we've got 1, 2, 3, 4, 5, 6, 7, 8, 9. 9 sets of coefficients plus all of the flexibility from the activation functions. So just imagine for a second, right? In our linear regression, we're like very constrained by a limited number of parameters to be able to manipulate the like functional relationship between x's and y's. And what we've departed from, right, in moving to the nonlinear territory is like, how have we given our model more flexibility to like move my line in weird ways, right? So polynomials, you add polynomials, and then in the splines, right, we have like knots that you can add. So you can imagine here, there's a lot more parameters to play with. There's all these activation functions that we can play with that that give our model a lot more flexibility. And so that allows you to be a lot, it allows you to build very complex relationships between your x's and y's. So complex, right, that we can't really explain it in the traditional way of where we just have betas. Now I'd have to explain all these, how it would work through these transformations and through all of these weights. But what that affords us is like much stronger ability to do predictions. There's a lot of parameters, a lot of flexibility. So yes, we are worried about, what are we worried about? If we add lots of variable, so before, if we were to add lots of variables, Overfitting, exactly. So in the machine learning world, they take this very seriously, right? There's a lot of mechanisms to try and be very careful about overfitting because that's a very easy problem to run into when you have this much flexibility. So cross-validation, all of that stuff is absolutely crucial in this kind of world. Okay, any questions about this? This thing right here, we don't actually observe, you typically don't observe this sort of as a piece of the outcome. And in fact, we call this thing a hidden layer, right? So it's a transformation that happens as an intermediate step between your inputs and your outputs, and we call that a hidden layer. So when I construct a neural network, what are the things that I have to mess around with, and how do I choose how to decide on some of these essentially parameters, right? So our fundamental question is how many hidden layers how many nodes / perceptrons. Okay. So number of hidden layers generically. So 0, this represents linearly separable functions. 1 approximates any continuous mapping in finite space. So I want you to think about that for a second. So all of the other techniques that we've talked about, right, like a polynomial regression, for example, or even the splines, right, there's only so much in so many ways that a line can move, right, and how as we give it more and more freedom, like it can oscillate a lot more, right? Think about this. With just one hidden layer, you can do a continuous mapping in any way that you could possibly conceive in finite space, right? So the line that you draw through your points can take any shape with just one hidden layer. 2, so 2 plus represents arbitrary decision boundaries. To arbitrary accuracy. That's with the correct activation function. Okay. So how many hidden layers should we use? I mean, generally, a small number of hidden layers is going to get you usually what you need. Like you generally will overfit very quickly as you add more hidden layers, and you'll find that in your out-of-sample cross-validations, this doesn't need to be a very high number. Like 1 or 2 layers is often going to be more than enough to do the job. Okay, so then the other question is how many nodes or perceptrons? And what I'll say right at the top is there's no agreed upon method. So, some rules of thumb that I have seen in various sources. So the size of, so one of them I've seen size of input layer should be greater than the number of hidden nodes. This should be greater than size of output. I've also seen rule where hidden nodes should be approximately 2/3 the size of our input plus the number of output layer sizes. Here are hidden nodes. Another rule I've seen, hidden nodes should be less than 2x the input. And then I've also seen this rule, number of hidden nodes is equal to our number of samples divided by alpha times our number of input nodes plus number of output nodes, where alpha is between 2 to 10. Okay? And just remember, more nodes is leading to overfitting. Okay, so these are 4 different rules that I have seen about like a rough rule of thumb for a number of nodes. And of course, this is an area that you can experiment a little bit and see how that, what that ends up doing to your cross-validation mean squared errors, right? We can use that as kind of really a guidepost for how many nodes to put in. If we actually look at our example here, I have 2 input nodes, 3 hidden nodes, and 1 output node. So of these 4 rules, which one have I followed? So size of input layer is greater than the number of hidden nodes is greater than the size of output. So this one doesn't follow that rule because I have more hidden nodes than I have inputs. So X and A on the first one. Hidden nodes should be approximately 2/3 of our output plus our output layer size. So 2/3 times 2 plus 1. So that would be 4/3, 7/3, so 2 1/3. So I have 3, so this doesn't follow the second rule either. Hidden nodes is less than 2x the input. Here we're okay, because 2x the input, there's 4, it would be 4, because there's 2 input nodes. 3 is less than 4, so okay. So we managed to follow one of these 4 rules. I can't say anything about the last one, because the last one is a little bit more unique, right? It's saying it actually counts the number of rows. This is a generic example. I'm not using real data, so I can't actually say anything about that. Okay? Any questions about this? Okay, so let's do neural networks in R. We're going to use ISLR again. I'm going to load in data table, and I already have ggplot loaded, so we're good there. We're going to use a data set called default. This data set has 10,000 observations, 4 variables. It's whether or not someone defaulted, whether or not they're a student, their current credit balance, and then their annual income. So we are going to look at whether or not if we're able to predict defaults based off of the other three variables. This is kind of a janky example. I'm going to change our data from yes, no into ones and zeros for the purposes of the neural network. So if it's yes, then it's 1, otherwise it's a no. And we'll do the same thing for whether or not they're a student. So we're going to change it to a number. If they're students, then 1, otherwise 0. Okay. And then I'm going to scale the data. I'm going to sort the data. And I'm only doing this to create a training set and a testing set. Just a slightly different way of doing it. Okay, so I now have a set of training data and a set of testing data from our default data set. And now I need one more library called neural net, which is the library that contains the package, it contains the function neural net, which is what we'll use to create our neural network. So our model we'll call default.nn for neural network. I'm going to use the neural net function. We're going to regress default on everything else using our training data. Okay. This parameter input into our function, hidden, you can probably guess what that stands for, right? These are our hidden nodes. And it is a vector where each entry of the vector tells us how many nodes in every layer, right? So what I'm going to do is I'm going to do hidden equals C2, 3, which means we're going to have 2 hidden layers. The first hidden layer will have 2 nodes. The second hidden layer will have 3 nodes. I'm going to choose to use a logistic function, activation function, and we will not have a linear output. Oh, hang on, did I miss logistic? Sorry, logistic. There we go. Okay, so let's plot this, and here we are. This is a graphic representing the neural network. Okay, so starting on the left-hand side, we have our inputs. student is the top node, balance is the next node, then income is the next node. We have the weights that were solved for, I believe via gradient descent, right? So these would be like kind of akin to the betas, except that these weights get transformed a bunch, right, through multiple hidden layers. So all these values here, these weights or these coefficients, they are numbers that you could plug in to give you prediction outcomes, but they're not interpretable in any way, like in the same way that we thought about how a beta is like a slope, right? This would be, this value and this value would be the slopes corresponding to this input prior to the activation transformation, right? So we can't say much about these individual numbers. But solve for everything, and then as I mentioned, we set it up so that we would have 2 layers, so 1 layer here, 1 layer here, with 2 hidden nodes in the first layer and 3 hidden nodes in the second layer. Okay? Solves all this stuff, and we get our kind of answer. So what's the point of making this model? Okay, running a little short of time, so I'm going to copy and paste some stuff, which you guys can reference later. But the whole idea is now I have a model that is able to do predictions, so I can feed in data. And remember, we already split our data into test and training sets. So I'm going to predict based off of our test set. And this will give me predictions on whether or not someone defaults or not. So we can look at the error rate, which is a little bit less than 3%. Okay? Yeah, and so that's essentially a demonstration of a calibrated neural network, and then feeding it some testing data, and then understanding how well it predicts. So here, the mean squared error, this is really just an indication of, right, it's because this is a classification example, it's telling us essentially how many out of 100 that it would get wrong. Does this model seem good to you guys? So only a 3% error rate, right? So maybe it seems pretty good, but the one caution that I'll give you, right, is that it really depends on the data. So suppose you have a 3% error rate, you have 100 data points of people defaulting or not. Suppose that only 3% of people defaulted, then I could have just guessed that nobody defaulted, and I would have a 3% error rate, right? So it depends on the baseline error rate. So you do want to check that. We can see the false negative rate is 2.4% compared to the false positive rate of 0.5%. And so if you care about that difference, you can actually calibrate your neural network to improve on particular portions of your error. And this is a concept that we've kind of mentioned before, but I'll kind of reiterate here. Okay, so that is it for today. That is our intro into neural networks. So I have another little lecture on convolutional neural networks that we can cover next time. But actually, I have some flexibility if folks are interested in other data analysis topics that we haven't covered that you'd rather do, just let me know, and we could possibly cover that instead. So I'll make an announcement about that, and then you guys can message me if you would like, if there's some other data analysis technique that we haven't covered that you'd like to see. Okay? Thanks, everyone, and I will see you all next week.